Okay, so this is an extension of the problem we looked at last time. You were probably not here. So we looked at this tree diameter problem. You're given a tree, and the diameter is defined as the distance between the farthest pair of vertices. So we saw how we could do this in linear time, essentially. Okay. Were you able to? Did you even manage to see the? You did see the video. Okay. Hey. So now we are given a further complication of this problem, where we are told that we can delete some vertices, and we want to keep the diameter as we want to make the diameter as small as possible by deleting k vertices, and we are given the number k. It's part of the input. So we're given a tree, we're given a number k, we're told that we can delete up to k vertices, and we need to make the diameter as small as possible. That's our job. Okay. So the output is simply the smallest diameter that you're able to achieve. That's all you need. Okay. So if we take this example, there are 4 vertices, and you're asked to delete 0 vertices, so you're not allowed to delete anything. So it's essentially the diameter problem. And this one goes 1 to 2, 2 to 3, 3 to 4, so it's a straight line. And you're asked, if you're not deleting anything, what's the diameter? So it's simply the diameter of this tree, and in this case it's easy. That's 3, and there's nothing interesting here. But in general, it could become a little more interesting, like in this case, where you're asked to delete 1 vertex out of 4, and you're told that the tree looks like 2, 3, 4, 3, and 1, 4. So what does that look like? You got 1, 2, 3, and 4. So we've got 2, 3. We've got 3, 4. And we've got, oh, it's still a straight line. OK, sorry. So it's just that the numbering was a little different. So it's still a straight line tree. And you're asked to delete 1 vertex, a leaf, in such a way that the diameter becomes as small as possible. So obviously, your only 2 choices in both of these bring the diameter down to 2. So I bet the answer is 2. OK. So that's all there is to it. Looks easy. The problem is that k can be horrendously large. K is not some small number like 1 or 2. We are told that k can be nasty. It can go all the way up to n minus 2. And you don't have to have n minus 2 leaves in your tree, because every time you delete a vertex, new leaves may be formed. So you'll always have at least 2 leaves in a tree. This is something that's known, right? So you'll always find something to delete, and so you may have to delete a lot of vertices. It gets worse if you have to delete, let's say, half the vertices, because then the combinations become very large, right? So what's a naive solution? What's a brute force solution? Let's start with that, even though you may have better thoughts for how to solve the problem. It's always a good idea to start with a brute force, just so that you know what you're trying to beat. Okay?
So maybe find the diameter, the 2 nodes,
yeah.
And then delete one of those,
yeah.
And do that 8 times?
Yeah, so that would sort of work. The only problem is that you may have a gazillion diametric pairs.
The worst case scenario is you take all the starting leaves, delete one of the leaves, and then do this recursively.
Right. So So you may have multiple choices for deleting in the first round, multiple choices for deleting in the second round, and so on and so forth. So each time, the first time you have n choices. Sorry, well, whatever is the number of leaves, so maybe that's n minus 2 choices. The next time, you may still have n minus 2, you'll have at least n minus 3 choices, and so on and so forth. Then you have to do this k times. So this is a very large number, especially when n is told to be 300, and k can be very large. So you have something like n to the power n over 2 kind of number. So this is not something, brute force is not something you want to try, but at least you want to understand that this is possible, right? Okay, so brute force, out of question. What else? We know how to do the diameter, right? Because that's what we discussed last time. Is there anything that we can do that'll help us? So since you're clear about the problem, let me close this and go to my slides. So let me give you some, well, let's set up the problem first. The diameter is the length of the longest path in the tree, right? And in this case, the problem has been made a little simpler. It's unweighted, not weighted. And it's undirected, that helps. And you're told what the values of n and k can be, how big they can be. And we know that the diameter can be calculated in linear time. And we're asked to find the minimum diameter. Oh, I'm not in the presentation mode. So we're asked to find the minimum diameter after k leaves are deleted. And you can choose whichever k you want. This is the problem setup. What do we know now? Yeah, we don't know how to pick the k leaves. So we've got to start with some ideas. Where do we even start? Any thoughts on what might help us? Yeah.
I was thinking of what you said last time about finding the center.
Yeah, that's right. So we talked about finding a center because center then helps you to figure out, okay, these are the guys that are far away. Let's start to delete them in some strange order. Good. So we could separately try and figure out how to find the center. But since we know how to find the diameter, we could do this where we say, the first idea is what Ricky said earlier. You find a diametrical pair, and then you delete one of the leaves, because each one's going to be a leaf. We know that for sure. So that doesn't work because there may be lots of diametrical pairs, right? So deleting one leaf may have no impact. It may not change your diameter at all, right? What's worse is that when you remove a vertex, you could create new diametrical pairs. That also is possible. How is that possible?
You might delete so many that now the diameter is another count.
Right, but are you clear about, so let's say that at this point there was only one, and suddenly you remove one, and could it become two? Right, so let's say that initially I had only one.
Yes.
Now I remove a vertex, a leaf. Can I suddenly have two?
Yeah, you can have that itself and another one.
How?
One less.
That's right. So can you imagine the tree?
Yeah. Like, I mean, oh,
No, you can imagine this?
Sort of.
Sort of. Okay, good. So for that, it really helps to think of this center thing, right? If you had a center vertex, here's the diametrical pair, and here's something else that's a little bit closer, right? And let's say you remove this guy. Now there's this guy's parent is one less away from the other end. So is that one now. So your diametrical pairs could actually start to increase. In fact, it could multiply. It could just go crazy, right? So that's another problem. We don't really know how to deal with them because we can't just say, okay, we'll just look at the diametrical pairs and start to work with this. That doesn't help you, right? So and we can't just take any diametrical pair and remove a vertex, because we know that many of these pairs, removing a vertex may not have any impact because there are other diametrical pairs, right? So how do I start to organize my thoughts here? That's the question. Yeah. So what about the center? Can we prove some properties of the center that'll help us? It turns out that there is one really important property that's going to help us. That important property is that every diametrical path must go through the center. You believe this? I had a lot of trouble believing it. I'm surprised you guys are happy to believe this.
My teacher told me once and I believed it.
Sorry?
My teacher told me once and I believed it.
So why can't I have, here's a diametrical path and here's another one. They don't touch each other. Why is this not possible? Why do they all have to go through that center vertex?
My guess is because then that wouldn't be a diametrical path because the real diametrical path would be connecting those two.
Very good, very good. Yeah, so let's say that, well, first of all, this is a tree. So these paths do connect to each other. So let's say that somewhere they connect to each other. All right? Now, you've broken up this path into two pieces. One of these must be at least as big as the other. Same thing here. Now, if I take the bigger piece of the two and I look at this path, that's going to be longer than your original diametrical path. So therefore, this can't happen. So that means that every diametrical path must touch each other somewhere. Right? Okay, so here's one pair, and here's the other pair. Now, can they connect anywhere? So if I look at this pair, and if I find the center is somewhere there, is that possible? Now, this is not possible because I could now choose between this and this. One of those is going to be longer than the diameter. So what we're saying is that it doesn't matter if the tree has more than one diametrical path, they must all go through some center. That's really what we are proving here. I didn't give you a formal proof, but I'm just giving you some intuition as to why that's true. Does that make sense? You're happy with this? So therefore, the center is something magical. Every diametrical path goes through there. And it's easy to find because once I find a diametrical pair, I just walk the path and find the middle guy. Okay, so this is my center. One minor detail is that the center may not be one vertex, it may actually be an edge because the path could be even length or odd length, right? Well, that's also easily handled because if it's not a single vertex, then I could do something like this. I'll make a fictitious vertex somewhere there and call that the center. Okay, I don't really care. And still, I can claim that every diametrical path should go through there. Okay? So I'll just throw in an extra vertex on the edge and fix the tree. All right, so this is what my tree looks like at the start. And now my question is, how do I start to delete leaves in order to shrink the diameter? And in order to shrink the diameter, the useful thing to know is that I have to start taking off leaves, but I can't just randomly pick whatever leaf I want. I have to be a little smart about it if I want the diameter to actually go down. Because if let's say that there are multiple vertices, all of these pairs form diameters, which one are you going to delete? The one on the left, right? Because if I delete this, it's going to impact every pair, and so I could reduce the diameter. Does this make sense? So we have to use ideas like this in order to make our algorithm smarter or correct. So how is that going to help us? Well, so it seems that if I have two subtrees, I could figure out how many are at distance half the diameter. I keep a count of this, and I do this on each side, and I always pick the smaller one, and unless I wipe out all of them, my diameter is not going to shrink. Right? So even on this side, there could be multiple, right? But as long as one side has more, I'll have to delete all these guys in order to shrink the diameter. Fine? Well, there is an additional problem now. That is that I don't have to have two subtrees. I could have many. So what if I have something like that? Now life gets even more complicated, right? If I have something like this, and let's say there are multiple branches here as well, and all of these are diametrical pairs, as long as they're in different subtrees. So this and this is a diametrical pair. This and this is a diametrical pair. This and this is a diametrical pair, and so on. As long as they're in two different subtrees, they're going to be diametrically. They're going to be a distance that's equal to the diameter. Now, how do I pick things?
You can delete the node with the fewest connections, the fewest branches.
Well, that doesn't help me because, remember, at the end, it may, there may be more vertices here, so the number of branches here is just one. It's just that hey, hi. I don't know if you understand why what you suggested is not quite working out.
Yeah, no, I understand.
Okay.
So I think considering that, then we would go into the subtree that has the fewest nodes.
Yeah, yeah. So so it turns out that we need to process this tree, okay, and make some decisions about which vertices we're going to throw out. We have to now show you. You need to come earlier. This is the problem we're looking at. It's called the diameter of the tree. And we did this last time where we showed how to find the diameter very efficiently given a tree. Diameter is the distance between the farthest pair of vertices in a tree. Okay? And we know that it can be done in linear time. Now the new complication is that we are allowed to delete up to k vertices, k leaves in the tree. And we need to, our job is to shrink the diameter to as small as possible. Okay? So you can delete things from the end and make this diameter as small as possible. So one idea is you find the diametrical path and then keep removing things from that path. That doesn't work because there may be multiple diametrical pairs in the tree.
Okay, so there may be multiple diameters at the same time, and just deleting something from one will not.
It's not going to help you. So now, because you're allowed to delete k, how can you smartly pick that k? How can you smartly pick the set of vertices that you want to delete in order to minimize the diameter as much as possible? That's the problem. So we figured out that one idea is to find the center of the tree. The center of the tree is something that's on every diametrical path, and the entire tree looks something like this, where you have a bunch of vertices that are half the diameter away, and now your job is to figure out which of those leaves you want to remove so that your diameter is reduced. So what we figured out is that the problem now gets complicated because the center may have many branches. And so here's the center, and it could have one subtree. If it has only two subtrees, you're in great shape, right? That's the best scenario, because then all you have to do is to delete one of these subtrees, and you figure out which one has the fewest nodes that are a distance half the diameter, right? So that part is easy. But if you have multiple, let's say you have three. Well, no, let's take four just to be. How do you pick which leaves to delete? Any thoughts on this? Yeah?
So if for each subtree we kind of store how many nodes at our distance.
Right. So let's say, yeah, that's right. So each one we already know that we have n1 vertices that are at distance half the diameter from the center. This one has n2, n3, and n4. So now what do I do?
First, you take the minimum of those.
You take the minimum of those, and
then after that, this new n number becomes the next level up. And we just want to consistently take the minimum of those.
right. So well, first of all, by let's say n1 is the smallest, and let's say I delete all those leaves from there. What's the new diameter?
It's n minus 1 plus.
What's the new diameter?
Diameter minus 1.
What's the new diameter? What's the new diameter?
Minus the number of nodes you deleted.
What's the new diameter?
Would it not be minus 1?
Why would it be minus 1? What about from here to here?
Oh, the max.
Remember, from here, this guy is half the diameter away. From here, this guy's half the diameter away. From here, this guy's half the diameter away. And from here, this guy's half the diameter away. If I only focus on the smallest one, and if I remove all the leaves, will my diameter be n minus 1? No, because there are a whole bunch of other pairs. Yeah?
Like I just want to make sure I
Yeah.
the center of the tree is where like is a place that all the diameters pass through, right?
Correct.
So what we're trying to do is to reduce that. So like let's say we have two subtrees.
Yeah.
And you mentioned that we delete them.
If it has only two, we're in great shape because we'll take whichever has fewer vertices that are half the diameter away. And I'll remove all those leaves.
Whichever has fewer
Yeah.
vertices that are half the
So actually, this is a good thing. Let's assume that we have a binary tree. So anywhere, any vertex only has two children. Okay? Great. So if that happens, then this scenario is not happening. I can remove two of these branches, right? So the center now has two branches, two subtrees. One of them has n vertices that are at distance half the diameter. The other has some other number of vertices that are at distance half the diameter. Unless I remove all of those on one side, I'm not going to reduce the diameter. That's clear, right? So I'm going to pick the one that's smaller. And since I have to remove k vertices, if k is smaller than both of these, then we're going to be done, because by removing only vertices on one side, we'll have an answer. Either it'll be -1 or it'll be the same. Right? But if k is larger than both of these, then I'll remove the ones that are smaller, and then I have to restart. Right? But then, how do I restart the process? What do I do? I have to find the new center. And the new center, fortunately, will only move in one direction. And in fact, I can move the center to here. Right? So I can start to move in the direction. So let's say I deleted these guys. So I move it in the opposite direction. And that's my new center. If it were here, and if I remove all of these, I'd move it over there. So I move half an edge every time I remove a bunch of vertices on one side. So I'll remove all of this. I'll figure out all the new vertices that are farthest away on this side. And then I would move the center and do the comparison again and figure out which one is more. And then I'll remove the other side. Does that make sense? So this is what works if it's a binary tree. Right? We just have to fix this for non-binary ones. Yeah.
So an idea for just general.
Yeah.
If we add all these n's,
Yeah.
n1 plus n2,
Yeah.
and so on.
Yeah.
And then we find the maximum of these.
Uh-huh.
Then if we add up all the n's, and then we subtract the maximum, and if k is bigger than this, then we can carry on to the next level.
Right. Correct. A simpler solution, you have it, but you made it more complicated than is needed, because if I have multiple branches, and let's say there's n1, n2, sorry, this is not quite working. So let's say this is my center. I have many branches. I have n1, n2, n3, n4, n5, number of nodes that are a distance half the diameter away. And just for the sake of argument, let's just say that this is the order. Okay, n1 is bigger than n2, at least as big as n2 is at least as big as n3, and so on. So now the question is, which ones am I going to remove? And according to you, you are going to add up a bunch of things and then compare it to k.
Yeah.
Which ones are you going to add? So really, the easiest thing to do is, if I add these up, that's going to give me the smallest sum. So I leave out the largest. I add up all the rest. If this number is less than or equal to k, I can remove all of these and then restart the process. Does that make sense? If it is not If it's equal to k, I'll remove all of these and my diameter will go down by 1. If it is less than k, if it's greater than k, then my diameter is never going to go down. So I can just report that and stop. Does this make sense? And then once you remove this, if there's still more things to remove, I will move my center in the direction where you have the largest branch. I'll move it half an edge, right, like before, and restart the whole process. But I do have to put in some work to figure out which ones are my new farthest guys. And it turns out that that's easy because it's just the parents of the leaves I deleted. Clear? So can we put this all together now? Little complicated. Are there pieces that you don't understand? Yeah.
When you say half an edge, you mean you're going to be creating a new node at the current center?
Right. So remember, I told you that there are two cases.
Yes. Yeah.
One is where the diameter is even, one where it's odd. If it's even, the midpoint will fall on a vertex. If it's odd, it's not going to fall on a vertex. It's actually falling on two vertices. So you can either write it down as two vertices, or you can write it as the edge that connects them, or you can make a fake vertex in between it. That's all implementation detail. We don't have to worry about it since we are only talking pseudocode, right? So if you want to imagine this vertex, if you want to imagine it as an edge, whatever you like, but that's your center now. Center sits on that edge. So I will move essentially the center. So if I remove all these guys, I'd have to move my center, not an entire edge, but half an edge.
Okay.
So it would go from there to there,
Okay, makes sense.
right? You're going to say something?
Can you repeat what you said after how we updated?
Yeah. So you now understand what it means to move the center. We'll assume that the number of vertices we've deleted is not enough. We still have room to delete more, happily, right? So what we're going to do is to restart the process. But in order to restart the process, I need counts again. Now, since you're in the middle of the edge, you have only two branches. This branch, the number of vertices that are at half the diameter away hasn't changed because we haven't touched those. But on the other side, we've gotten rid of everything. But in the process of getting rid of everything, we now have a bunch of vertices that are one less away from these, and those are going to be exactly half the diameter away. And those vertices are exactly the parents of the vertices you deleted. So you take all the vertices you deleted, go find their parents, and those are your new vertices that are diametrically far away, and count those. That's the number you need. And you're never going to be left with anything, because when you cleaned up, you better clean up the entire set of leaves, right? So you can also be sure that when you clean up the leaves, the parents are now leaves. You have to show that. The parents are going to be leaves because if they had something left over, that guy is going to be diametrically farthest, and so you could not have left that in, right? Am I making sense, or is this going too fast?
So like after you delete like from n minus 2 to
Yeah.
n equals that, right?
Yeah.
You shift the center by
You're talking about this picture or this picture?
no the picture we did right.
This one.
Mhm.
Yeah.
So you deleted,
I deleted all these leaves.
which reduced the total diameter by 1, right?
It reduced the diameter by 1, that's right.
Okay. So what you do next is you shift that center.
I shift that center half an edge away.
Which then
So the diameter is now d minus 1 divided by 2. If d was even before, now it becomes odd.
Which makes the new leaves the n minus.
The parents of these leaves that you just deleted will now be exactly half the diameter away, right?
And then you repeat the same process.
Then you repeat the process. Are we cool? It's not that easy, but it's very, very doable once you figure out how to compute the diameter and the diametrical pair, right? So remember, you're not trying to find all the diametrical pairs. Don't bother doing that because that's too much work. So what you do is you find one diametrical pair, find the center because that's easy, and that center is the magical center. Okay, and that's what we convinced ourselves. This magical center is fabulous because it's the magical center for all the diametrical paths. And that is, unless you understand enough of the theory, that is hard to figure out. And that's what makes this problem hard. Okay? You're still unhappy? You're okay?
No.
Yeah, you're good?
Yeah.
Okay, cool. Let me see what else I have here. So you find a diametrical pair. If you delete one vertex, the problem is there are too many other diametrical pairs. So this doesn't work. So I'm just going through the thought process for you, recapping. Yeah. So deleting one leaf may have no impact. So that's why we have a problem. Also, many new diametrical pairs may get created, and we have to kind of keep track of this. We don't know how to do it. At least we didn't know how to do this when we started thinking about this. And we came up with this key observation that's critical to all of what we discussed, and that is that all paths must pass through a single vertex that we'll call a center. I call it a midway point here. It doesn't matter. Call it the center, right? That requires a proof. That's not trivial. But as long as your intuition is good on this, you should be able to figure that out. So here's the approach that we ended up taking. You find a diametrical pair. We know that that distance is d, because that's what the previous algorithm will tell us. Then find the midpoint on this, find the center of this path. That's easy. You just walk down the path and find one that's right in the center. It may be a new vertex. It may be a vertex or it may be an edge. So there's that little thing we have to take care of if d is even or odd, right? So that part is easy. Now, once we find this new center, we can do breadth first search from here, because breadth first search will tell us how far away these vertices are, right? And we can label all of them. So everything is now labeled, and we just find all the vertices that are at distance d over 2. We sort of process this tree bottom up so that for each branch we know how many vertices are farthest away from the center, and we send that information right up to the top. So we end up with a situation that looks like this. For the center, we have a bunch of branches. Each branch, we know exactly how many leaves are at distance half the diameter away. That's what we figure out when we process this tree bottom up. And then we delete the leaves that are at distance d over 2 from all the subtrees except the one that has the most. That's what we said. This one has the most. We delete the leaves from all the other subtrees. Is that clear? Then we check. So this is half the algorithm. So yeah, this is what we did on the previous slide. We deleted all the leaves from all the subtrees except the largest one. Then we make the parents of these leaves that we just deleted. We make that the new frontier, right? And we move the center half an edge. and then we move, and then we simply repeat the process. Well, before that, you have to check whether you've already deleted k vertices. If you haven't, you keep going. Okay? So, time complexity.
Would be n times k.
N times k. Okay, that seems like a reasonable way to start, because you're doing order n operation every time, and you have to do this at most k times. Each time you're going to delete at least one vertex, so that's how you get n times k. But I don't really have to do all the processing over and over again, because I don't have to find the diameter once in my next iteration. So that saves me that order n time. Then I don't have to find the number of vertices in each of those branches, because all that has been figured out. And so I may be able to save something, right? Is it clear that it is n times, as bad as n times k? Could it really be order n? That's the question. You're understanding what the question is?
Yeah, I think I understand.
Okay.
Like we're doing n work, we have to do n work at least 2 times to find the center. And
Which
then
is fine. That 2 times n is still order n, yeah.
And then after that, we start reducing, like from down, we start reducing and then going up.
Right.
Until k becomes 0, which is also.
Well, we just go back to the top and figure out which one's the largest, and we delete the leaves from all the others, right? Deleting the leaves doesn't have to be explicit. You don't have to go and physically remove them if you don't want to, but you could conceptually remove them. You just have to keep track of the new leaves, right, that are farthest away. And so you go to each of those leaves that you're going to delete, go to its parent, and label those as the new leaves, right? And you now have, and you would have figured out how many new leaves there are. Once these are removed, those are never going to figure back into your calculation. And so you don't have to look at them again. Your number of vertices has now reduced. And so you have new parents that may have to be deleted next, but they will essentially become part of the list of vertices list of leaves that you're interested in. So you have to manage some data structures. I'm not saying this is easy, but I need to convince you that this whole thing can be done in linear time. That's what I'm trying to do next.
But aren't you like doing almost linear work after every single time you delete, trying to figure out which one is the maximum?
Right. So that's a good question, and that's what we need to worry about. Right. So let me try and redraw this, and maybe we can try and convince ourselves. Okay. Let's see if we can work this out. Here's our current center, right? And it has many branches. In each branch, so let me draw one of the branches in some detail. So let's say these are the ones that are, yeah, that's good. So let's say these are the vertices that are half the diameter away from the center. Okay. On this side, again, I have some bunch of things. I should probably draw that too. Let's say you have something like this, okay? So it's now clear all the leaves that are part of diametrical pairs, right? So what do we know? We know where the center is currently, and we know, so we'll do breadth first search from here and we'll label everything, right? So when you label it, this guy is going to be 0, all these are going to be 1, all these are 2, all these are 3, all these are 4. That's clear, right? Then I need counts. I need counts of how many are there. So at this point, I know that I have 3 vertices, right? Here I have 2, here I have 2, here I have 2, then here I get 3. So let me use a different color, unfortunately, otherwise I'll mess up. Okay, so here I have 1, 1, 1, 1, right? This is 3, this is 2, this is 2, this is 2, this is 1, 1, 3, 1, 3. That's what I have. I'll move that information up. This would become 5. This would become 4. This is 1. Oh, am I missing? Do I have one less vertex there? Yeah, I need to put in one extra vertex there. Okay. Yeah, I hope I got that right. So this is still 1. This is 5 and 4, 9. This is 1, 1, 1. This is 7. This is 7. So now I have the center with 4 subtrees. The number of leaves that are relevant for us is 9, 1, 1, and 7. Right? So I'm going to keep the ones that are at distance 9 because that's the largest subtree for me, right? I'll delete the leaves from all of these. So we need to figure out what we want as well. It doesn't matter what k is. Let's just assume k is very large. So we're going to try and delete the leaves from here. All right, good. So we know that we want to delete all these guys. Perfect. When we delete them, the parents of those guys are going to be the ones that are relevant. So what do we do? How many did we delete? We deleted 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've deleted 9 in the first round, right? And now I have to update, well, you're right. So I have to update all the numbers, which means this is going to become 1. This is still 1. This is still 1. And this is going to become 3 now. This is going to become 3. And that's what goes up. I still have 1 there. I still have 1 there. Nothing else changes. So I can now delete the next round, which would be all of these, right? So I end up delete 1, 2, 3, 4, 5. So in the second round, I would delete 5. And I'll check whether that's enough, whether I've reached my value of k. But you're right, I do end up processing this all the way to the root. Well, I don't have to process this information all the way to the root. I just need to know how it changed over here at the bottom level, and I can send that information directly to the root. So first of all, when I deleted this, the center moved here. And now I only have 2 branches, so I only care about what this total is. I don't care about anything else. So as long as I know how much it changed, I'm going to be in good shape. I deleted 9, I created 5, which means that this number, which initially was 7 plus 1 plus 1, it used to be 9. I deleted 9, but I brought back 5. So over here, I'm going to say it's 5 that's going to the new center. So my new center is here, and it has 2 branches, and the number of, so I'm writing that in green. So the number of leaves that are relevant from this branch is 3. Is that clear? Sorry, not 3, 5. Because that's 1, 2, 3, 4, 5. So this side I have 9, that side I have 5. I know which one to choose. I'm going to delete the 5. So I delete the 5, and now I'm left with 1, 2, 3, and 4. So 5 becomes 4, and I can do that without having to do the linear time processing. All I'm processing are these leaves. It's true that that could be linear, but then once I process it, I'm throwing it away, so they're not relevant. Right? So when I look at all the leaves that I'm processing as I go up, I can take care of that. Now there is one other problem that I pushed under the rug. The problem is that when I delete the second level, what happens? My center moved some more. So now the center is here, and now I have an extra branch. So now I have to do that calculation again. I have a branch with 5, I have a branch with 4, and I have a branch with whatever that tells me, which in this case 5 became 1, 2, 3, 4. It became 4. So I still have 4. And now I have a new center that's here, but that is looking like this. On this side I have 5, on this side I have 4, on the other side I have 4. Okay? So I do have to, I did need this information clearly over here in order to process it correctly. Now could that happen? Yeah. So I think we're still in good shape, because as we go down, new branches may come up, so I have to do this calculation over again. But every time I do the calculation, I throw away the leaves from that branch. Are you guys comfortable with the solution? Does it look like it'll work for you? And are you convinced it's linear time? That's the hard part. Well, even if it's not linear, even if it's n times k, n is only 300 and you're in good shape. So you don't have to worry about it. In fact, you could just redo the whole algorithm from the start, and who cares? It'll work fine. It's just that you could actually squeeze a little bit more here. Yes?
Isn't it possible, because I'm assuming after we move the diameter and we end up at a...
You mean the center?
Yes, I'm sorry, the center, and we end up in a place that includes a new branch.
Yeah.
We'll have to do like a new depth first search to update it.
No, well, because we have all that information. We did that once. So that information hasn't changed because you haven't touched this branch, right? You never touched that branch. But you're right. So I'm going to say it's somewhere between n and nk. Yeah? Either one is good because k is still only 300. And 300 times 300 is just, what is it, 9,000. Sorry, 90,000. No big deal, right? So is this a good problem for Saturday? Yeah? I don't have anything else for you. There was a problem. What time is it?
10:30.
10:30. Yeah, we should probably stop. Yeah, let's stop here. I still have to prepare my class for these guys here.
Today's the review.
Today's the review, yeah. So I should prepare a little bit for the review. Is that okay? Sounds good?
Thank you, Professor.
Thank you.